This lecture is going to go over the concept of how to determine the oxidation state of an atom. So this is part of one of our types of classifications of chemical reactions, and this is particularly important for oxidation reduction reactions, and these are reactions in which one or more electron are transferred between reactants. So let's start off with an example, and the example we'll look at is this reaction shown below between copper solid and our silver plus cation. In this reaction we form copper 2 plus and silver solid. So if we examine this reaction a little bit more, one of the things we can see is that copper is starting off as neutral copper and it goes to copper 2 plus. And so in order for that to happen, the copper had to lose 2 electrons along the way. And silver started off as a cation and ends up as silver metal. And so silver had to gain an electron. And one of the things we see here in these redox reactions is the total number of electrons lost has to equal the total number of electrons gained. And that's the reason why in this reaction we need 2 silvers on both sides of our reaction arrow to normalize the number of electrons lost and gained. Now, in these redox reactions, these oxidation reduction reactions, we need to develop a sort of system to keep track of electrons so we can quickly identify which atoms have gained electrons and which atoms have lost electrons. And that system is the oxidation number, also called oxidation state. So this is a bookkeeping method used to keep track of where electrons are and where they're coming from and going to. In general, the oxidation number of any atom is just the difference between the number of electrons in the neutral atom and the number of electrons in the atom as it exists in a compound or ion. So let's go through some examples of determining oxidation number, and then we'll come up with a general set of rules to help us assign oxidation states. So the first set of examples we'll look at are these atoms here. We have metallic copper, metallic iron, O2, and P5. And when we look at all of these elements, what we see is the first two, copper and iron, these oxidation numbers are 0, right? These are neutral atoms. They have not gained or lost electrons. And with the O2 and P5, these are the elemental states of those elements, oxygen and phosphorus. And again, it's all the same atom, so these are all neutral, and so the oxidation number is 0. So our first general rule for determining oxidation state is that whenever you have a single type of atom present, whether it's copper or O2 or P5, the oxidation number is always equal to 0. If we switch it up just a little and we start to look at ions, we can look at copper 2 plus, iron 3 plus, O2 minus, and F minus. So here, when we look at these, take copper 2 plus first, we can say, well, copper lost 2 electrons. And so going back to the definition, right, the difference between the number of electrons in neutral atom and the number of electrons exists in the atom, in the ion. We say copper lost 2 electrons, so the oxidation number is plus 2. For the iron 3 plus, that iron lost 3 electrons, so the oxidation number is plus 3. And then our anions below, these have both gained electrons. So for O2 minus, the oxidation state or oxidation number is negative 2. And for fluoride, it would be negative 1. So our second general rule we can use is that monatomic ions, the oxidation number is always just equal to the charge. Now things get a little bit more complicated if we look at a molecule like nitric acid, HNO3. And when we're confronted with atoms like this, sometimes we have to go through a series of steps to determine the oxidation number. And so those steps would be, first we'll start off with the Lewis structure. So I'm going to go ahead and draw the Lewis structure of HNO3. And when we draw it, it's going to look like this: a central nitrogen bound to 3 oxygens, double bonded to one of the oxygens, and one of the oxygens is bound to a hydrogen. Now, when we count electrons for our oxidation number, what we're going to do is we're going to assign all of the electrons in a covalent bond to the more electronegative element. So this is different than our formal charge counting. It's similar, but it is different. Here, all of the electrons go to the more electronegative element. So I'm going to color code our molecule and say oxygen's more electronegative than nitrogen and hydrogen. And so what I've done is color code, and in this case, all of the electrons actually go to the oxygen atoms and none to the nitrogen or to the hydrogen. Now what we're going to do is we're going to go through this calculation, and we're going to calculate the difference between the number of electrons in the neutral atom and the number of electrons we assign to it in our structure. So when we go through this, we can start off with nitrogen. Neutral nitrogen has 5 valence electrons, and we've assigned 0 to it in the molecule because all of those electrons go to oxygen, so 5 minus 0 is plus 5. So the oxidation state of nitrogen here is positive 5. If we go to the oxygens, we can take any of those oxygens, shown in red, and we see that each oxygen has 8 electrons assigned to it. There's 6 electrons in neutral oxygen, so 6 minus 8, so each oxygen has an oxidation state of minus 2. And then for hydrogen, 1 valence electron in neutral hydrogen, 0 assigned to it in the molecule, so hydrogen has an oxidation state of plus 1. The last thing we should do is just make sure that the sum of all of the oxidation numbers of all of the atoms is equal to the charge of the molecule or the ion. So we're dealing with a neutral molecule, so if we add up all the oxidation states, we should get 0. And so indeed that's the case, where we have 3 atoms with a -2 oxidation state, your oxygens, nitrogen's positive 5, and hydrogen's positive 1. So if we add those together, we do get 0. So if we do enough of these examples, we can come up with our general rules to help us assign oxidation numbers quickly. And so here are our set of rules. Atoms in the pure elements have an oxidation number of 0. Monatomic ions have an oxidation number that's equal to the charge of that ion. So that's like copper 2 plus has an oxidation state of plus 2. Oxygen almost always has an oxidation number of -2. The only exceptions for this are when oxygen is in the elemental state, O2, or if it's in a peroxide where you have an oxygen-oxygen single bond. We won't see those very much in this course, so for our purposes we can say oxygen will have an oxidation state of -2. Fluoride will always have an oxidation number of -1 if it's bound with other atoms. Hydrogen always has an oxidation number of +1 unless it's directly bound to a metal. With these short set of rules, we can usually assign the oxidation number of almost all atoms in a molecule if we just then know that for all other atoms in that molecule, the sum of the oxidation numbers has to be equal to the total charge. So if it's a neutral compound, the sum of the oxidation numbers is 0. If it's a polyatomic ion, the sum of the oxidation states have to equal the charge of the ion. With that, you should now be able to assign oxidation states to atoms in almost any molecule. Thank you.